In this video, we're going to build up towards the expectation maximization algorithm, or EM algorithm. And I'm going to present it in quite a general way because it turns out that the EM algorithm will be applicable to many different latent variable models. So throughout this, we're not going to assume at this stage that we have a mixture of Dowson's clustering model. We're just going to assume that the model comprises of latent variables, S, N, which are generated from some underlying parameters, theta, and then observations, X, N, are going to be generated from those latent variables and the model parameters. And that's really all we're going to assume. So any model that is written like this will be compatible with the equations which follow. The EM algorithm, as I said previously, and in particular, the objects that we're going to use to derive the EM algorithm, the variational free energy, lead to a variety of different extensions that can handle complex models via something called approximate variational inference. And throughout these slides, I'm going to slightly simplify the notation, otherwise the slides will get very heavy. In subsequent lectures, we'll sort of go back to the old notation, but for the minute, in order to make it clearer what I want to focus on at each stage, I'm going to use the following notation. So our set of observations, all of our x's, I'm going to collect them together and just notate them as a single vector x, okay, with no subscript on it. And similarly, our set of latent variables here, for all of our data points, I'm going to collect them together into a single vector of latent variables with length n. That will just denote the collection of latent variables. So in particular, on the next slide, we'll see that the log likelihood, which we took some time to derive in the last video but one, the log likelihood we can substitute in our vector notation for this guy, and so it becomes just simply log p of x given theta. And similarly, if I want to show application of the sum rule, where I write the marginal probability of x given theta in terms of the sum over the joint probability, I'm just going to notate that like this, where that sum means summing over all possible settings of the latent variables. Great, so this is just some notational shorthand to keep things easy to parse as you read the slides. Great, okay, so our first step towards deriving the EM algorithm is going to be developing a lower bound to the log likelihood. And the algorithm will actually operate on the lower bound rather than on the log likelihood directly. And the way that the lower bound is going to be created is going to be kind of simple. We're going to take our log likelihood and we're going to subtract off it a quantity which is a type of KL divergence, which is why we needed to learn about KL divergences before we saw this video. So what participates in the KL divergence? Well, we're just going to take the KL divergence between an arbitrary distribution over class memberships. So this Q of S here is a probability distribution over the latent variables S. Is going to be one of the things that the EM algorithm refines. And in particular, we're going to take the KL divergence between it and this thing down here, which is the true posterior distribution over the class memberships. It's P of S given X and theta. This is the thing that we talked about computing in order to do the soft clustering. It's the probability that data point N comes from each one of the K clusters, given the observation of that data point X and the model parameters theta. Okay, so this is clearly going to be a lower bound, because the KL divergence, as we talked about extensively, is non-negative. It's either zero or a positive quantity. And this lower bound is called the free energy. This is because it connects to a quantity in statistical physics called the free energy. Technically, the free energy in statistical physics actually has a minus sign in front compared to this definition, but machine learners seem to be, well, they are notoriously sloppy, and that's often been forgotten a lot of people, and so this is often labeled the free energy itself in machine learning. It's the log likelihood minus the KL divergence between Q, this arbitrary distribution over class membership variables, and the true posterior distribution. Okay, so far this construction looks a bit arbitrary and it's perhaps not clear where we're going, but just bear with it a minute and we'll see how this leads to something which is useful algorithmically. First off, some sort of mathematical properties that this bound has, which it inherits from the properties of the KL divergence. Firstly, we know that the KL divergence, as I said before, is always non-negative. And so it's definitely true that the green thing, the free energy, is always going to be below or equal to the true log likelihood of the parameters. So it's in general a lower bound on the log likelihood of the parameters. That's not rocket science. Notice also that when the KL divergence is 0, so when Q is equal to P of S given X and theta, we know that when the two arguments of the KL divergence are the same, it will evaluate to 0. And at that point, the free energy will be tight. It will be equal to the log likelihood. And we're going to rely on these two properties over the next few slides in order to construct an algorithm for optimizing the parameters theta, finding the maximum likelihood settings of the parameters theta, or in general, converging to a local optimum of the likelihood. And at the same time, the algorithm is going to operate on the free energy rather than operating on the log likelihood itself. Why might we do that? Why might we want to operate on the free energy rather than the log likelihood itself? After all, it has the log likelihood in its definition, the way we set it up. Well, it turns out it's rather easy to rewrite the free energy in a simple form that means it doesn't explicitly have to evaluate the log likelihood and the KL divergence in order to compute it. We don't have to evaluate this blue term up here and this red term. Instead, we'll show in a couple of videos time or a video's time that you can write the free energy out in this really easy to evaluate form here, shown in green. And this is easy to evaluate because it's just going to depend on P of S given theta, which is going to be related to our pi's in our model, if you think about the clustering example, or in general, just our prior over the latent variables, and P of X given S and theta, which is in our clustering model, the Gaussian distribution over the X's with mean mu and covariance sigma. So this will depend on the Gaussian cluster probabilities in the clustering model. In general, it will just be the conditional distribution, which is specified in your generative model. So both of these terms here inside the log at the top are specified in our generative model to start with. They're not things we have to compute using algebra or any other sort of calculation. So they're naturally specified in the generative model, and it means that the free energy is easy to compute. So as I said, in a video's time, I'll show you how to do this, to go from the definition at the top to this second, much easier to evaluate form of the free energy. I don't want to get bogged down in algebra at this stage, so we'll return to it after we've built some intuitions for what the free energy is. So these two views, though, are both important. We have this first view at the top, which is the view that's often easiest to use to understand the properties of the free energy. And then we have this view number 2 down here, which is the view that we essentially need to operate with on a computer because it's easier to compute with. So these are both perspectives of the free energy that are sort of independently useful. Great, okay, so far, lots of definitions, a bit of mathematics. Let's start to talk about how we can visualize the free energy and then use that visualization in order to come up with an algorithm for finding maximum likelihood parameters. Okay, so here's a slide where we're going to do that. And first off, I'm going to show you rewrite for you so you don't have to remember it, the definition of the free energy. It's just the log likelihood minus the KL divergence. And the canonical picture that you'll see in many textbooks of this is the following one. We can visualize the free energy as a function of the parameters down here. So here's the free energy as a function of the parameters. I've evaluated the free energy for a particular setting of this arbitrary distribution Q over the latent variables. I've called that Q naught. And then I'm just going to vary theta. and trace out that curve. And we know by definition that then will sit below the KL divergence. Sorry, but below the log likelihood, and the amount that it sits below the log likelihood at each point will be the KL divergence between Q0 of S and the true posterior for that setting of the parameters theta. So at some points, the free energy might be quite tight, the KL divergence term will be quite small, and for other locations in parameter space, the KL divergence term might be quite big. But in general, the green thing is going to be a lower bound. So this is what you'll see written in textbooks, just to sort of schematically show you that the free energy is a lower bound on the log likelihood. Here's my favorite picture of the free energy, and it's a bit different. In this way of visualizing the free energy, we're going to view it as a function of two arguments. Firstly, parameters on the bottom again. So we've got theta on the bottom, and we're going to imagine varying the parameters of theta, and seeing how they affect the values of the free energy, just like we did on the left-hand side. But now on the y-axis, I'm going to imagine varying q as well. So the free energy depends on this arbitrary distribution. And I'm going to imagine along this axis, I laid out all possible settings of that Q distribution. So this is a schematic where we can do that, but this would obviously be a hard thing to actually compute with. But let's just sort of carry out this sort of schematic cartoon representation where along this axis here are all possible different ways we could have set Q to, and we can evaluate the free energy for each one. And these things here are now the contours of the free energy function. They show lines of constant free energy. Great, okay, so hopefully the two schematics are clear to you. And what I now want to think about is how the left-hand side relates to the right-hand side. How does the two-dimensional schematic relate to the sort of the 1D plot on the right-hand side? And that is kind of easy to see. If I pick along this axis here, the part of the axis where Q is equal to Q0, and then I took a horizontal line through here where I valued theta for a fixed setting of the distribution Q0, I will trace out this curve. Okay, so the curve on the left, we can view it as a horizontal slice through the free energy on this 2D schematic where I have fixed Q to be equal to Q0, and then I vary theta and I trace out all of the points on the left-hand side here as I move from left to right across this line. Great, okay. So each horizontal line through the free energy essentially defines a different lower bound on the log likelihood. Now I want to think about the converse slice through the free energy on the right-hand side. I want us to think for a minute about what happens if we fix the value of theta to theta star. And now I'm going to trace a line vertically and vary Q to all possible settings of Q. And in particular, what I want to think about is if I maximize along that line, if I find the maximum point along this vertical line here, maximum is going to appear here where the contours are indicating we're near a peak. What value will Q be at that point? So what setting of Q will actually maximize the free energy? And I also want to think about what the value of the free energy will be at that point. Okay, at this blue dotting here, what's the value for the free energy? And remember, we've got the definition of the free energy at the top here. So what I'd like you to do is, to spend 30 seconds just thinking through this question, eyeballing the free energy and just getting comfortable about what the solution is to this. Great, so I hope you've thought through this. Now, the right answer to this question is the following. So we know that the free energy, the only way that there's Q dependence in it is in this KL term here. So if we're optimizing the free energy as a function of Q, then the only place it appears is in this KL term, and the optimum will be to set the Q equal to the true posterior distribution for that setting of the parameters theta star here. So this is the optimal setting of Q that maximizes the free energy. And at that point, the KL divergence is equal to 0. So we can just forget about this part of the free energy, and the free energy will evaluate to the log likelihood at that point. Everywhere else, the KL divergence will be positive, and so it will take away from the log likelihood, and the value of the free energy will be a bit below it. But at this maximum point, the two things are equal, and so the free energy is equal to the log likelihood for that setting of the parameters. And that is an absolutely key fact which we can use to construct an algorithm which optimizes the log likelihood, the blue curve on the left plot here, but only ever operates with the free energy. And in order to do that, I can sort of now tie these two plots together in a really concrete way. So in particular, this point here that we've just been talking about corresponds to this point here on the log likelihood, where we evaluate the log likelihood at theta star. We know that because we've just specified that mathematically on the right hand side here. So this point here corresponds to this point here on the log likelihood, and at that point the free energy is just touching the log likelihood. Now I could make this argument for any vertical slice. I could have taken a vertical slice here, and at that maximum point would correspond to another point on the free energy, say here, theta star star, theta star star, the free energy. At this point here, the maximum for this vertical slice would line up to this point on the log likelihood. And so there's a locus of points here where I carry out a vertical optimization at any point in the free energy that defines the log likelihood. And so I've just labeled those on the right hand side here. So the free energy along this line here evaluates to the log likelihood. Great, okay. So here's how the EM algorithm is going to work. Let's just move some of the clutter. What we're going to do is we're going to initialize the parameters of our model, our latent variable model, to theta naught. And we're going to initialize this arbitrary Q distribution to Q naught. And that will leave us at this point in the free energy shown by the dot down here. So we've initialized theta naught, we've initialized Q naught. And what we are now going to do is we're going to optimize in the vertical direction. So we'll optimize along this light green line shown here. And we know that that's going to land us being here on the log likelihood, on the point where the free energy is equal to the log likelihood. So let's carry out that optimization. And at that point, we've evaluated this log likelihood. Here's our initial setting of the parameters over here. And the free energy is evaluating to the log likelihood, so we're tight. So that optimized the parameters optimized the Q distribution with the parameters fixed to their initial value. We're now going to optimize in the horizontal direction. And we know that this will trace out a lower bound on the free energy, that's shown over here. And we'll optimize along that horizontal line to find the most probable setting, the value of the parameters that maximizes the free energy. And that gives us this dark black point here. And that corresponds, of course, to this black point over here, the optimum of that horizontal slice through the free energy. And now we want to get us back to being tight to the log likelihood. So we're going to optimize over the free energy again in a vertical direction. And that brings us back to the locus of points shown in blue here. And gives us a new setting for our distribution Q over the latent variables. And then we optimize it in a horizontal direction again. That traces out another lower bound that's shown over here. You can see that slowly but surely, these lower bounds are getting closer to the maximum in the log likelihood. The maximum in the log likelihood is here. That's our maximum likelihood setting the parameters that we're looking to find. But we're slowly improving the log likelihood. We're finding parameters with higher and higher log likelihood value. And as things progress, you can see that this coordinate-wise optimization of the free energy, if we carry on repeating it here, that will eventually converge to this peak, and that will give us, maybe after 10 iterations in this case, the maximum likelihood settings of the parameters. When the parameters don't change anymore, we can quit, and we know we'll have computed the optimum value for the free energy, and the optimal value of the free energy, because the free energy is a lower bound, is also the optimal value of the log likelihood. So this idea of carrying out coordinate-wise ascent on the free energy is called the EM algorithm. For historical reasons, optimizing Q is called an expectation step, because you're changing the expectations of the latent variables, or expectations of quantities involving the latent variables. The optimization of theta is called the maximization step, because you're obviously maximizing the parameters. Notice that this is really similar to the picture we had in our minds for the k-means algorithm, where we recast it as an energy optimization procedure. Optimizing in a horizontal direction here for k-means was changing the centers of the clusters, and optimizing in a vertical direction for k-means was changing the assignments. Here we have optimizing in a horizontal direction changes the parameters of the model, which will include the cluster centers, and optimizing in a vertical direction is altering sort of the soft assignment of data points to clusters, i.e. Setting Q equal to the posterior distribution for that setting of the parameters of the cluster memberships, given the observed value X and the current setting of the model parameters. So hopefully this is sort of connecting back to the ideas of the k-means algorithm. We'll make those statements and intuitions mathematically really precise in a minute. So in the next video, what we will do is we'll mathematically go through these steps that we've just been talking about. We'll explicitly define the EM algorithm, and then we'll implement it and talk through the calculations that we require to implement it for a simple mixture of Gaussians model, and we'll make the connection to the k-means algorithm absolutely explicit.